4/3 pi times little r cubed. Okay. Oh, yeah, this should be, sorry, cubed. So this cancels out, and we get q enclosed is equal to q times r cubed over big R cubed. All right, so then we go back to Gauss's law. Gauss's law said that this was equal to q enclosed over epsilon naught. Kind of put this to the side over here. All right, q enclosed, well, that's big Q times r cubed over big R cubed. So I'll go ahead and rewrite this. I get E4 pi r squared equals q enclosed, so that's going to be q times r cubed divided by r cubed, big R cubed. All right, and I get that canceling out with that right there. I solve for E, and I get E equals 1 over 4 pi epsilon naught times q over r cubed times r. And that means that the E field increases as you get farther away, unlike out here where it decreases as 1 over r squared. Here it increases as r, so linearly as you go out. And if you wanted to plot this, you could plot this, and it would look something like this. Here is r. This is your electric field. It grows linearly as you get up to there, and then it decreases as 1 over r squared as you get farther away. That's, oops, r. All right, so that's Gauss's law. There is also some Gauss's law questions on the quiz, which I will give back tomorrow, and I will go over them tomorrow. So you'll get more Gauss's law tomorrow. Yes?
When you're doing the smaller circle, does little r change? Obviously, it's not going to the bigger circle on the outside. Right?
Mm-hmm.
I just
This is in general, right? This is for any little r that's between 0 and big R.
Okay.
So you just pick one in general that's right here, but really it means that it's any size.
Okay.
Okay? Because that's the electric field at this point right here.
Right.
But if I make it smaller, then it's the electric field at that point right there, and I can make it bigger up to that surface, and then after that surface it changes to this one right here. And then you can find the electric field there, and I can make it bigger, and so on, as big as I want out to infinity. So you get to choose, but this tells you in general. And for this particular problem, there was 2 cases. Now the one on the quiz, there was 3 different cases, right? There's nothing inside the smallest one, so the electric field in there is 0. That's the other thing. Anytime there's no charge inside your Gaussian surface, what's the electric field? 0, okay? Farewell. Thanks. So if you have a Gaussian surface and there's no charge in it, the electric field in there is 0. That's it. Yes?
If little r equals big R, then which one do you use?
They give you the same answer. So you can use either one. Right? That's kind of a weird place, but they'll give you the same answer. Yes?
So on the quiz, the ball with the sphere on the quiz, the charge was on like the outer edge, but in this case, the charge is on the inside of the sphere, so it's like charging slowly.
No, in both cases, the charge was evenly distributed through the volume.
Okay.
So, like on a conductor, which brings me to a good point. Right? You can use Gauss's law to tell you about conductors. Right? All the charge on a conductor resides on the outside of the conductor, right? On the very outside. So if you take a Gaussian surface in the middle of your conductor, how much charge is enclosed? 0, right? If you have 0 charge enclosed, Gauss's law says that the field inside is 0. So here, E has to equal 0 since Q enclosed equals 0. So, but in that, and the one on the quiz, there was some, I'll redraw it. It was like this. There's no charge in the middle here, so it's a hollow sphere with no charge there, and then the rest of this had charge equally distributed about it. So it's an insulator with charge equally distributed about this. Yes?
So any conductor is only going to have charge on the outside of it?
Yep.
Even if it's a solid conductor?
Even if it's a solid conductor. Yep. And if you, so what's the field inside of a solid conductor?
Zero.
It's zero. It's zero. And Gauss's law will tell you that really quick. Okay, because Q enclosed is zero. All right, other questions about Gauss's law? It's always going to be something like this. Now we did other examples. We did a line charge, in which case you use a Gaussian surface that's a cylinder. We did, I don't know if we did it, but you may have done it in the homework, or there's definitely examples in the book of a plane of charge. And for the plane of charge, you can use, well, you can use a box, or you can use a little cylinder that's extending. As long as the electric field lines are going through perpendicular or tangent to the surface, you're good to go with Gauss's law. And I'll do more Gauss's law tomorrow in lab when I give you back your quizzes. Okay, we've got 5 more minutes left. And then I turn into a pumpkin. But we're getting into more recent material, so. Okay. Chapter 28. We'll talk some more about this tomorrow. We'll be on the exam. Homework 28, or chapter 28 homework is going to be due on Wednesday. It was supposed to be due on Monday, but I didn't get as far as I would have liked on Friday. So I'm extending that to Wednesday. Yes?
We have a quiz in that tomorrow.
Yes. It's going to be a half-assed quiz. So it will be poorly written, it'll be easy, and it'll be easy to grade.
Okay. Good.
So just no quiz.
Yeah, and if you take that case into the limiting case, that would be no quiz. So that is a possibility. Depends on how much stuff I get done tonight, because I also have a 141 exam to grade. Yeah, yeah. It's at least I only have 1 instead of 3. 3 classes of 141 exams. That was like 1,000 pages I had to grade every time I gave an exam, which was brutal.
Why give exams?
That's a good point. You know, why give exams? Everybody just shows up and learns, and it's like idyllic, and we go out, we do cartwheels afterwards. It'd be great. All right. That's right. Chapter 28, this is potential energy. And I won't talk about this that much because we just kind of recently went over last week and we're still in it. Potential energy and this thing called the electric potential. No, it's stupid. It's like calling the electric field the force field and the force is called a force or something. It would just be stupid, right? I guess a force field is a thing in science fiction, right? A force field. Whatever. It's science fiction. Maybe that's where this came from. Anyway, the electric energy and electric potential. This is actually electric potential energy and electric potential. They're 2 different things. They are related, but they are different. One is measured in what? What's potential energy measured in? Joules, like the energy we know and love. And then electric potential is measured in volts, named after Alexander Volta. And it's a related quantity, right? It does tell us about how potential energy is changing, but it's kind of weird. Now, it's analogous to electric fields and forces, right? The reason why we have electric fields in the first place is because we want to talk about how forces act on particles, right? If you have a charge here, it distorts the space around it. It creates an electric field, and then that electric field applies a force to a charge in that field, okay? And then that force points in some direction, in the direction of the electric field, right? This is analogous to that in the fact that we have this thing called potential, okay? And it surrounds the charge. And if you put some particle in there, it's going to have some potential energy, okay? Now, the difference between this and the electric field, okay, if you have, you don't have an electric potential field. And the reason why is, what does a field imply? What is a field? Yeah? Someone said something? No? Kind of. They're both things that are kind of stored in space. But, all right, how would you draw an electric field? Okay, yeah. Now, right, if I have some positive charge here, I want to draw the electric field. I go out here, and I draw this right here. That represents the electric field in space right there. What is that? It's a vector, okay? A field is a bunch of vectors in space. That's what the electric field is. It's a vector at every point in space, and what it tells you is if I put a positive charge there, it's going to move in that direction. That is why we have an electric field. It's a vector field that tells you which direction the charge is going to move. Okay? Now, electric potential is sort of the same thing, only it's a bunch of scalars in space. So you go to any point in space and you say, aha, that's 10 volts. What does that mean? That means if I put a charge there, it's going to have some amount of potential energy. Okay? So you get the potential energy from the electric potential the same way you get the force from the electric field. And it turns out to be almost identical the way you do it. But this is much more convenient, and the reason why this is much more convenient is because it's a bunch of scalars in space as opposed to a bunch of vectors in space, which is much more difficult to calculate. So there's an analogy to be had here. One is the vector quantity, one is the scalar quantity. Now, the electric potential energy, that's equal to Q times E times S. For this would be like a particle in an electric, or in a parallel plate capacitor. So you have a bunch of positive charges over, actually no, it's the other way around. You have a bunch of negative charges over here. You have a bunch of positive charges over here. Okay, this is S equals 0 at the negative plate. Your electric field points like this in this direction. And if you move to some region like this, we can say the potential energy at this point S is equal to that right there. So that's for a uniform electric field from some parallel plate of negative charge like that. That's how you would calculate the electric potential energy. Now, we did some examples of all this in class, and I'm kind of out of time, so I will talk a little bit about this, but I would look at the notes and the examples that we did in class of how to calculate and use conservation of energy for this, right? We had 2 or 3 examples we did on Friday. Potential energy diagrams. Those are important, right? And the potential energy diagram for a parallel plate capacitor like this would be something like this. It's a straight line. The energy is totally linear. For the electric potential energy between 2 point charges, it's either going to look like this, or it's going to look like this, depending on whether they are attractive or repulsive. So know the potential energy diagrams for these, and the slope of this is, the negative slope is the force. All right, I don't really have much to go over. Everything else in this, we did like last Friday. And then we have a little bit more to go over tomorrow, so I'm gonna call it quits for tonight. We'll go over a little bit more tomorrow and Wednesday, but nothing that I go over on Wednesday will be on the exam. Just the stuff that I go over on Monday. All right, thank you guys.